Hi, I'm Cooper. So last year I was on the Pioneer Fire, and it seemed like everything that we did was kind of at the wrong place and at the wrong time. And it seemed like there was a lot of trouble trying to map out where this fire was going to go and when it was going to be there. So I kind of became curious to see if I could create a program that could model the spread of wildfire, at least in two dimensions. So I looked around the internet a little bit and I found this system of differential equations. So these equations are really great. They do exactly what I was hoping that they would do. This here models the temperature at any point in space and time as the wildfire progresses. And this here models what's called the fuel mass fraction. So that's how much fuel is left at a point in space as the fire progresses and how much fuel will be eventually left in the end. And that just comes with this small stipulation here that says we're not going to be considering the fuel to actually be disappearing until we've reached this ignition temperature. So fuel is not going away unless things are actually burning. So while these equations are really awesome, they present a lot of really challenging difficulties. If you have any experience with differential equations, you might notice these are high order, and they're high order in all dimensions of space. They're also nonlinear, and they appear in this coupled system. So both of the variables that we're trying to solve for depend on one another. And not just on one another, they also depend on a bunch of independent variables of space and time. So the way that these equations are set up, a closed form solution may very well not even exist. And if it does exist, it will probably be nearly impossible or impossible to solve for. So instead of trying to achieve that closed form solution, we can try to just approximate these equations really, really well. And we can do that with a method that's called a finite difference technique. So I've written a script here in Matlab that utilizes that finite difference technique and applies it to the differential equations that I showed. So it does that by first discretizing the entire plane that the fire is going to burn across and then time stepping that solution forward. So I'm going to publish this code in the description of the video, but I'd like to show it running. So you can see it starts with these spot fires here, and the wind is pushing down towards this bottom left-hand corner. So you can see the fire is going to continue to spread and get hotter until it reaches sort of this critical point at which it's consuming the fuel at the fastest rate that it's going to be able to. At that point, the heat's going to start to diffuse and it's going to start to cool off and die back. And that's starting to happen now. So the fire is going to continue to do this until all the fuel has been consumed or it runs out of time. I've set a maximum time step on it. But you can see it's cooling off. Awesome. So here's the final fuel distribution. This is how much fuel is left at the end of the fire. And if you compare that to the initial fuel distribution, you can see that there's quite a bit less. This yellow area, that represents sort of a 100% fuel distribution in that spot. So if the fire had been allowed to continue to burn, it would have eventually consumed all the fuel until there was none left, and it would have gone completely out and black and cold, just like a real wildfire. So that's it. Thanks for watching. There's a few more improvements I'd like to make on this project. Obviously, if I could get topography involved and make this happen in 3 dimensions, that would be really great. Right now, that's not going to be possible with the computer that I'm using. It's going to overwhelm my computer for sure. So that's it for now. Thanks for tuning in. If I make any more improvements on this project, I'll update the video.